Imagine the sheer, massive challenge of teaching a machine to drive safely at highway speeds. It's not just about slapping a camera on a dashboard. It's about building a real-time, highly accurate perception and control system that can take absolute visual chaos and somehow translate it into safe, split-second driving decisions. Today, we're diving into a really fascinating explainer on an autonomous driving pipeline built entirely in MATLAB. We're going to look at how combining cutting-edge deep learning, specifically YOLOv4, with classical geometric image processing, the Hough Transform, creates this incredible system for real-time vehicle and lane detection.
So, here's our roadmap for today. We'll start with seeing the road ahead, move into AI meets geometry, tackle the math of movement, and finally wrap up with real-time autonomous performance. Let's get right into it. Section 1. Seeing the road ahead. Every great system has to start with capturing and prepping the raw visual data. Right, so to build a robust training and operational workflow, the system follows a very strict set of steps, from raw video to final visualization for every single frame. Step 1, load the video frame and resize it to match YOLOv4's exact input dimensions. Step 2 is applying camera intrinsics. Then we hit Step 3, which is absolutely crucial, pixel normalization and data augmentation. By normalizing those pixel values, we're essentially helping the YOLO algorithm converge faster and learn a lot more effectively. We also throw in data augmentation, things like flipping the image or tweaking the brightness, because the model needs to be tough enough to handle the unpredictable, chaotic lighting of the real world. Only after all that is the frame finally outputted to the detectors.
Now, you might be wondering about that second step. Why are camera intrinsics so vital? Well, think about it. If you skip loading these intrinsic calibration parameters, you literally just have a flat, meaningless grid of pixels. Intrinsics provide the critical mathematical mapping between a flat 2D image and the actual 3D real world. Without them, the vehicle's brain has zero way to accurately judge if an obstacle is 10 feet in front of the bumper or 100 feet away. It is quite literally the foundation of the car's spatial awareness.
Section 2. AI meets geometry. Now we shift from just looking at the image to actually understanding what's in it. This is where modern deep learning intersects with classical image processing. It's a real divide-and-conquer approach. On one side, we have YOLOv4. This is a neural network operating as our dynamic hazard recognition system. It hunts for other cars, draws those familiar bounding boxes around them, and its accuracy is graded by a metric called mean average precision, or MAP. On the other side, we have the Hough Transform. No deep learning here, this is classical image processing. It acts as the spatial boundary manager by using the canny edge detection method to lock onto static lane lines. Its performance is measured by intersection over union, or IOU. So one system handles the dynamic chaos of traffic, while the other maps the static, geometric rules of the road.
But let's be real for a second. What happens when conditions aren't perfect? How does this setup handle terrible lighting, other cars blocking the view, or those awful worn-out road markings we've all had to drive on? If the Hough Transform needs clear lines to work, what does it actually do when the physical road degrades?
The answer is all on the pre-processing and filtering logic. First step, the system drops the RGB frame down to grayscale to save on computing power, and then applies a Gaussian blur. This acts like a filter to wipe out visual noise. Think rain or gravel on the road. Next, it dynamically adjusts the Hough parameters so it can actively search for faint, barely there lines depending on variable road conditions. And here's the real game changer. It applies strict geometric constraints. The algorithm mathematically knows what a lane should look like, so if it sees a weird shadow or a guardrail, it filters out those false detections to keep the vehicle safely centered.
Moving on to Section 3, the math of movement. Our simulation knows where the cars are and where the lanes are, so let's talk about how it actually steers. It all begins with lateral control. For your basic lane keeping and simulated lane-changing maneuvers, the system relies on a proportional controller, or P-controller. The math here is remarkably elegant. The steering angle simply equals Kp, which is our proportional gain, multiplied by the difference between the lane center and the vehicle's actual position. It just calculates how far off center the car is and tweaks the steering wheel proportionally to nudge it right back into the safest spot. But Okay, when things get a bit more intense, like maintaining safe following distances or pulling off smooth high-speed maneuvers, the system brings in the big guns, Model Predictive Control, or NPC. This is a highly advanced optimization loop. Instead of just reacting to an immediate error like the P controller does, the MPC algorithm looks at real-time lane and vehicle data to predict a safe reference path over a set time horizon. It actively minimizes heading error, lateral deviation, and sudden control effort all at the exact same time. And that means the ride isn't just safe, it's actually smooth.
And to make those future predictions possible, the system leans on the kinematic bicycle model. These core equations represent the vehicle's state. X and Y represent your position on the road, driven by velocity and the angle of your heading, theta. That heading angle is figured out using the car's wheelbase, L, and the steering angle, delta. And of course, velocity is dictated by acceleration, A. These discrete formulas are the exact mathematical rules governing spacing control between vehicles and all those complex lateral adjustments.
Finally, Section 4, Real-Time Autonomous Performance. Let's look at the actual numbers to see if this MATLAB Simulink pipeline actually holds up in practice. 20 milliseconds. That is the blazing fast average inference time per frame for this entire setup. And why does that matter? Well, for smooth, real-time autonomous driving, you generally need to be running at 30 frames per second. That gives you a strict maximum budget of 33 milliseconds per frame to make a life-or-death decision. By hitting 20 milliseconds, this YOLOv4 and Hough combo easily clears that hurdle, leaving plenty of crucial computational overhead for trajectory planning. And the best part? It doesn't sacrifice accuracy to get that speed. The vehicle detection hits an 85% mean average precision score. Meanwhile, the lane detection hits a really impressive 90% intersection over union score. It's an incredibly fast, highly precise pipeline. On top of that, the tracking system maintains phenomenal spatial awareness during trajectory planning. The standard deviation in position estimation is a super tight plus or minus 0.1 meters. Think about that for a second. When this vehicle calculates where a hazard is, its margin of error is basically the width of a human hand. Which leads us directly to this final performance metric, a 92% overall state estimation accuracy. This really proves the system's reliability and predicting the dynamic, moving parameters of the cars around it. It's not just seeing them in the moment, it's predicting exactly where they're going to be a fraction of a second from now, with 92% precision. But we do have to remember the context of the source material. As the findings conclude, further refinement in integration of realistic vehicle dynamics and environmental constraints are necessary for real-world applications. Basically, this flawless MATLAB simulation is an incredible foundation, but it leaves us with a really provocative question. What new, chaotic environmental variables have to be solved next to take this perfect math out of the simulator and onto the wildly unpredictable, messy physical city streets? It's a massive challenge. Thanks for exploring this source material with me, and we'll catch you next time.